Okay, good afternoon, everyone. Welcome to this last appointment with Rediscovering the Space, our cycle of inspiring speeches for the PhD program in Aerospace Science and Engineering at Politecnico di Bari. At the end, let me say that this cycle of seminars has been a real marathon with an unexpected wide participation by PhD students and colleagues. So I sincerely want to thank our very kind and respectable speakers. They come from different areas of the aerospace field. They gave very clear and inspiring talks, allowing us to have a global vision of the problems around the aerospace. I want also to thank Professor Francesco Cupertino, our rector, for supporting this initiative and compatibly with these many commitments, attending almost all the events, fortunately. And finally, I also want to thank the colleagues that helped me and worked as moderators of different events, and also all the participants. So, to end with a flourish, today I'm very pleased to host two brilliant colleagues, Alfonso Pagani and Marco Petrolo. They are professors of aerospace structures and design at Politecnico di Torino, and then we talk about uncertainty quantification and damage analysis for aerospace structures. I really thank Alfonso and Marco for being here, even during this hot summer period, and for their contributions to this cycle of seminars. Please do not hesitate to ask questions after the talk, after both the talk at the end. So finally, I give the floor to Maria Cinefra. She's also a professor of aerospace structures and design, but here at Politecnico di Torino. She collaborates with Alfonso and Marco, and she will be the moderator of the event today. Thank you, Maria. Thank you, Alfonso and Marco.
So thank you, Marco. Of course, it is my pleasure today to introduce these two speakers that were my colleagues at Politecnico di Torino. They belong to the research group MUL2, that is the research group led by Professor Carrera at Politecnico di Torino. They are both associate professor at Politecnico di Torino, and even if they are very young, they have an extensive experience in not only at Politecnico di Torino, but also in other prestigious universities in the world. Indeed, Alfonso, first of all, gained his PhD at Politecnico di Torino, but in collaboration with the City University of London. Then in 2019, he earned a prestigious research project that is the ERC Starting Grant about a new approach to the design and modeling of composite materials with variable stiffness. And he spent a period as visiting researcher at California Institute of Technology, where he was working about the modeling of acoustic metamaterials, and he also spent other periods in other universities, as the Purdue University in 2016, and if I remember well, also at RMIT of Melbourne. Also, Marco Petrolo was a researcher. He gained his PhD at Politecnico di Torino, but he spent also a period as a researcher at RMIT of Melbourne. And during his PhD, he spent also different periods in US, in particular at the university, at San Diego State University and the University of Michigan. And at the moment, he has different prestigious collaborations with other universities, as to mention the most relevant, the British Columbia, the University of Washington, and also he collaborates with NASA about the topics that today we'll present. So these are just a few points that I can mention about their work, and I suppose that in the presentation that today we will see, they will present other details about their activities. So I can give the floor to my colleagues, and good presentation.
Thank you. Can you hear me well? So thank you, Marco and Maria. We are very happy to be here today. So I will give the first part of the presentation on the multi-scale modeling of composites, with particular attention given to failure and progressive damage analysis. Before starting, I want to acknowledge a few of my colleagues, in particular Professor Carrera, who is the leader of our group, and Dr. Khalil Nagaraj, who were PhD students here in Torino.
Sorry, Marco. Sorry, yep. Marco, sorry. Could you increase the volume of the audio?
How is it now? Is it better now?
Okay. I ask to the others to confirm that they...
What about now?
Okay.
I hear Marco very well.
Okay, great. Thank you. So as I was saying, I want to acknowledge my colleagues, in particular Professor Carrera, who is the leader of our research group here in Torino, and Dr. Khalil and Nagaraj, who were PhD students here in Torino, and now they are doing their postdoc in the United States, were involved pretty much into the topics I will talk to you today. So this is a basic outline for today. So I will give you a brief introduction on our research activity in Torino and composite materials more in general. And then I will give you a brief overview on the structural theories we have for composite, in particular for composite and aerospace applications. So what we will see today is mainly focused on aerospace application. And finally, we will see some results on failure analysis and multi-scale analysis. This is a hot topic, research topic in these days. So let's start with a brief introduction of our research group. So as Maria said, we work at the Multi group in Torino. Professor Carrera is the leader of the group, and we have some 20 group members, including 4 faculty members. We have quite a few European projects running. We deal with different topics, and we have a nice network of collaboration around the world, basically mostly in Europe, United States, and China. Our main research activity deals with the development of structural models. And to do so, we use the Carrera Unified Formulation. This formulation was first proposed by Professor Carrera some 20 years ago. In a nutshell, can be seen as a framework to get any structural theory in a unified manner. So with this framework, you are free to implement any structural theory without virtually no constraint. And this is important for many applications. And today we will see how this might be good for composites. And on the right hand side of this slide, you can see the capabilities that we have in our finite element code. So part of our research activity is with the development and the writing of a finite element code that is named Multi after the name of our research group. And we have quite a few capabilities for the virtual testing and manufacturing of composites. For instance, we can run failure analysis, multi-scale analysis, and recently we have been also starting working with process simulation, in particular with the computational residual stress due to the curing process of composites. Today, we will see a few of these capabilities. And today, the aim of my presentation is to provide very general guidelines on the proper selection of a model. So let's say that you have a structural problem to solve, I would be happy to give you a few guidelines on the structural model to use for that particular model. The choice of this model basically has to take into account two main things. First, the accuracy, and then the computational cost. So usually when you build a numerical model for a structural problem, you have to deal with these two aspects. And usually higher the accuracy, higher is the computational cost. So you have to do a trade-off between these two constraints. I won't give you many theoretical details because there is no time for that, but feel free to ask more details in the Q&A session that will follow, or just write me an email. I will be more than happy to answer. So let's start with some basics on composite materials and structures. So just to be sure to be on the same page today. So in general, composite can be defined as a union of two or more constituents with different properties. And these constituents remain separate and distinct within the final structure. In aerospace, the typical example is given by the union between carbon fibers and a thermoset resin. Moreover, in aerospace, usually we start building the composite from pre-preg. Pre-preg is pre-impregnated solution of resin and fiber. And then this is used to create the final part. And usually this step is the material deposition, and there are many solutions for that. One of the most common in the aerospace industry is the automated fiber placement, as Alfonso Pagani will tell you later on today. After the material deposition, we need the curing process. To do so, we use an autoclave to apply pressure and temperature. This is a very important process of the manufacturing, as we will see today. And again, in the aerospace industry, for instance, to build a wing, to build a composite wing, the typical combination is the pre-preg plus the automated fiber placement plus the autoclave. So this is the typical combination you use for the composite manufacturing in aerospace. And with these techniques, you can build many primary structures for aerospace applications. As you may know, the most famous right now are the primary structures of three airplanes, namely the 787, the 777-9, and the A350. 787 and A350 have more than 50% in weight of composites inside them. 777-9 is a bit less than that because in 777-9 the fuselage is still in aluminum, but the wings are both in composites. Why we do like composites? Well, they are lighter than metals. They lead to a faster assembly. So basically, with composites, you may need a few days to assemble the final aircraft. With metals, you may need weeks or months. Another good thing is that with composite, you can tailor the properties of the structure itself. So you have way more freedom into building, into designing your structure. Of course, there are issues to solve. One of these is the numerical modeling. So the numerical modeling of composite can be more difficult than metals. One of the reasons for this is that the composite, the nature of composite is a multiscale, as we will see later on. And then another big issue is related to defects. So we have defects, for instance, from manufacturing or from in-service problems. And these defects are difficult to deal with and may lead to failure. So it's important to study them and to find a way to handle these defects. So the first part of the presentation is a brief overview on the structural theories we have to model a composite structure. So before starting with the theories, I think it's useful to give you a basic terminology just to be sure that the terms I use are those that we all know. So from now on, I will refer to 1D, 2D, and 3D theories. These are the classical structural theories based on beams, plates, shell, and solid models. And moreover, I will refer to classical theories when I will talk on Euler, Bernoulli, Timoshenko, Kirchhoff, and so on. So those models that we all studied in second year course at the university. Then I will introduce refined or higher order theories. These theories are all those that go beyond classical ones. So all those theories that relax in a way or another the assumption of classical theories. A very famous one is the third order shear deformation theory. So the aim of refined theories is to provide better results than classical theories. For instance, by removing assumptions such as those related to the shear deformability. As we will see, shear deformability is very important in composites, so it's important to have a model that is able to model this kind of mechanical behavior. When I refer to a model, I will refer to the degrees of freedom as well. So the degrees of freedom is the number of unknown variables. For instance, in Timoshenko, we have 5 degrees of freedom per node. As we will see, higher the order of the theory, usually higher the number of degrees of freedom. So you get more accuracy, but usually you pay something. This fee, let's say fee, is the number of degrees of freedom you need for your computational model. In general, we can define the structural theory as a set of mathematical relations and assumptions. The aim is to reduce the 3D problem in a 2D or 1D. Why we need that? To reduce the computational cost. So the 3D problem is not always endable by the current computational capabilities. So we still like 2D or 1D models for reducing the computational cost. And as I said, the general framework we use for this is the Carrera unified formulation. So why we need a refined theory for composites? Because composites have physical properties that are more troublesome than metals. In particular, we have high transfer shear normal flexibility if compared to metals. We usually have a discontinuous layer-wise physical distribution of properties through the thickness. So layer by layer, when we consider a composite, we may have very different physical properties. And this is something that have to be taken into account in our structural model. For instance, this discontinuity brings us to very complex displacement distribution along the thickness and stress distribution. So I don't go too much into details into this aspect because there is not enough time, but this is a very peculiar aspect of composites that drive most of the development of structural theories. Moreover, there are a lot of scenarios in which there are even more complicating effects. So whenever you have to deal with composite, you would like to compute many outputs. For instance, the residual stress from the curing process or the analysis of progressive damage. All these mechanical behavior are very difficult to model and require very accurate structural models. This is just a few numbers to give you an idea of what we need for higher shear deformability as compared to metals. So here we have just the ratio of Young moduli and shear moduli and the comparison with between metals here on top. So usually we have a number that is in the range of 3, and composite. In case of composite, we easily can have 100. So this is one of the metrics we use to define this shear deformability. So this is just a very simple case in which you can see how the shear deformability is way higher in composites. So you need to take into account in your model. And as I said, the other issue is that composites are multiscale. This means that if you want accurate results, sometimes you need to take into account more scales. So usually we can have at least 3 different scales. We have the structural or macro scale. Then we have the mesoscale, in which we consider each lamina. And then we can have the microscale, in which we model each fiber and matrix. So depending on what you are interested in, you have to deal with one or more scale. Of course, if you are interested in the global response, the macro scale is just fine. So you don't really need to go into much details. But then if you instead are interested in damage, let's say the lamination or the bonding, you have to consider each lamina. So you need at least the mesoscale, and so on up to the microscale. Of course, more scales you consider, more difficult it is the modeling and higher the computational cost you need. In this slide, you can just see a few models that we have available for modeling the different scales. We go from the equivalent single layer model, that is the one that is more efficient in a computational standpoint, but it is usually good enough for the macro scale. If you want to model the mesoscale, at least you need a layer-wise model. Layer-wise means that you explicitly model each layer with its own set of unknowns. This means that you need higher computational cost, but you get very good accurate stress field. And then so on up to the component-wise approach, in which you can model each single component at the microscale. So again, I don't go too much into the details of this. If you like, we can talk about this later, or you can contact me for that. Let's see just a few numerical results. This is a typical assembly for a space structure. So in particular, we are interested in this area in which we have a joint between 2 different composite parts. So in this area, so this is a cross-section of what we have on the left. So on the right, we have a cross-section. As you can see, there are different materials with different geometries and a lot of discontinuities, geometrical discontinuities. So this is just an example to let you see how complex the stress field can be around that area. And you can see the stress field in these 2 pictures. So first of all, you have all 6 components of stress that become important. So you need both the in-plane and out-of-plane stress field in order to have good accuracy for these models. And then you have very high gradient in the area of the constraints. So in this area, you can see a very high variation of stress in a small area. And to do so, either you use 3D finite elements or refined structural models as those that we have available in our code. Another example of physical behavior that is very difficult to model in composite is the free edge. So a free edge is, the free edge effects take place at the interface between the similar layers and in the vicinity of geometrical or mechanical discontinuities. So let's suppose that this is a composite plate. So in this area, so at the end of the plate, if we have the similar layers, say different orientation, we may have a free edge effect. Free edge effect means that you have a 3D stress state, and in that area, the stress values are very high. And we can see this in this example. So we have a wind box with some openings, and now we focus on one of these openings, In particular, we focus on this area here, so at the very end of the opening, so where the free edge can take place. In this plot, we have the stress components. The red one was taken just before the free edge. The blue one is just at the free edge. So as you can see, you move a few millimeters and there is a huge jump in the modulus of the stress state. So this means that in that area, you can have very high stress field and failure may occur. Why failure may occur? Because in composite, we have a very complex failure behavior. So we can have different failure mechanisms depending on what you are considering. So if you consider fiber, matrix, and so on, you may have different failure mechanisms. The main tool that we have to detect failure is the failure index. The failure index is basically a combination of the stress components in a point. So they are built in such a way that give you a number. If that number is larger than 1, this means that in that specific point, you may have a failure. And that number comes from a combination of the stress components. For instance, in this example, this is a typical aerospace component in which we have a stringer and a plate. We may have failure, for instance, in this area, because this area, again, is an area in which we have the free edge effects. This is the area in which there is the discontinuity between the plate and the stringer. And you can see this effect in, this stress state in these plots here. In particular, in the first two plots, I show you the failure index that was computed via the Ashin 3D criterion. And as you can see, this point is where the free edge is. So in this area here, or point A here. So as you can see, there is a huge increase in the failure index in a very small area. So this is just a numerical example that tells you how important it is to model this kind of structure in a proper way to detect this potentially very dangerous behavior. So with failure index, you can detect where the failure takes place. Then you need to study how failure can progress. So now we talk about damage progression. So as you have the first point in which failure takes place, then failure can increase. So we have a propagation of the failure. And that's what we mean by damage progression. So the ability to track failure and to see how a failure area propagate into the composite structure. This is a very difficult phenomenon to model. This is a nonlinear analysis because we have a degradation of the material properties. So you need a nonlinear analysis to take into account this kind of phenomenon. Also, the models you have change as soon as you consider different failure mechanisms. So you need a model for compression, you need a model for tension, you need a model for delamination. So all this put together makes your damage model very complex to deal with. There are different approaches to deal with this problem. The one that we have in our virtual platform use a combination of continuum damage for the intralaminar damage, so the damage that occurs in plane in our ply, and discrete modeling to deal with the delamination, so the delamination between different plies. And this is a typical example that you can run with a progressive damage model. So this is the low velocity impact in a plate. So you have an impactor, this red ball, that simulates the low velocity impact that you may have in service. So this is a typical incident that you can have during your during the life of your composite components. And the typical results that you can get from a virtual platform are the time history of the impact force, like this on the right. But even more important is the damage distribution. So in this slide, you can see how the damage propagates due to the low velocity impact. And here you can see the impact related to the fiber. So these are the fiber damage under compression. Here we have the matrix under compression. So in a virtual platform for the progressive damage, at the end of the day, you end up with this kind of results. And these are important to, for instance, modify the design of your composite plate or to track the progression of the damage inside your component. In order to get even more accurate results, sometimes you need to model different scales, as I said. And this is because the composite nature is multiscale. So each scale has different properties and tends to influence the other scale. So if you want to model some very complex scenarios, you need to deal with the multiscale feature of composite. To do so, the first thing you do is dealing with the micromechanics. So the idea here is to take a representative volume element of your composite. I will show you what I mean by RVE soon. So you take this element as a representative of the architecture of your composite, and you focus on that to extract properties and mechanical behavior and transfer that to the entire structure. So this is an example that should help you to understand better what I said. So basically, instead of considering the entire composite, we consider this volume here. So this square here is our RVE, in which you have a number of fibers and some metrics. So we consider this as a representative of the entire composite. And then we run static analysis on this kind of structure. And we get the stress field along this RVE, and then we transfer this stress field to the macro scale, as we will see soon. We may have different architecture. For instance, on the right-hand side, you can see the typical architecture of a honeycomb for sandwich structure. So the RVE technique can give you the freedom to deal with different architecture for different composite structures. And these are the a few examples of numerical results that you can get from this kind of analysis. For instance, the progressive damage along the micro scale. So the progressive damage we saw before was at the layer level, so along each ply. Now we can get the progression of damage inside the matrix along the fiber. So this is just an example of how deep you can, the depth of results you can get with a micromechanical analysis. Or you can insert defects. For instance, in this case, we inserted voids inside the matrix. This is a typical defect you can get from manufacturing. And we then studied the effect of these defects on the stress field. So in these plots here, you can see how for different percentage of voids from 1% to 5%, you have different stress values. Different means that you can get a variation of also 20%. So higher the number of voids, higher the maximum stress field that you can get. Then you put all these things together and you build your multi-scale approach. In a multi-scale approach, you have basically at least two different models. A model for the macro scale. So let's say that this is the model we saw in the first part of the presentation, and a model for the micro scale. And you let these two models communicate to each other. So you have communication between these models in order to pass information from one model to another. Doing so, you can run this kind of analysis. So basically, you have the macro structure, in this case, a plate with a hole. You insert a macro load, for instance, tension, and then you build another model, so the RVE, and transfer the information from the macro scale to the micro scale. So you can get the stress field at the micro scale starting from the macro scale analysis. And on the right hand side of this slide, you can see a typical example of that. So you can see how the macro field on top is transferred to the micro field on the bottom. And this is very important to have very accurate, for instance, failure analysis. So in this case, you can see which part of the resin, for instance, may fail, and then you can modify your design accordingly. Before closing, if you are interested, I suggest you to go into the details of this platform, that is the NASA Multiscale Analysis Tool, or NASMAT. This is the new state-of-the-art multiscale framework of NASA, in which you have what I presented here today, but even more capabilities. Basically, they are collecting many multiscale and micromechanics models and putting them together. And even more interesting is that they can deal with an arbitrary number of length scales. Today, I show you examples with just 2 length scales. I named them macro and micro, but in a more general way, you may have more length scales, and that's what they do in NASMAT. So if you're interested in multiscale analysis, I really suggest you to go through this platform because it's very useful and very powerful for your research activity. So I think I'm already using more than what I was supposed to do. I now close my presentation and give the floor to my colleague Alfonso Pagani.
Thank you, Marco. We'll try to share my screen. Hopefully you can see. Okay. First, I would like to thank again Professor De Tullio and Professor Cinefra for inviting us. And I'm really proud and happy to give this short talk about our research activities on aerospace composites. And this second presentation will deal particularly with stochastic mechanic analysis of what we say variable angle toe composites, in which you will see it's a new class of composite materials, which is very attractive for aerospace. Of course, the work I will be presenting is not my own work. It's not just my own work, but is the work of a research group. And Marco, Professor Petrolo, has already discussed research group, so I will skip this slide. So I'm part of the Multu group, of the Multu lab at Politecnico di Torino. And as researchers, and we are also involved in promotion, in promoting aerospace culture and events. We do so through AIDA. AIDA is the Italian Association of Aerospace, of Aeronautics and Astronautics. And it is one of the most important, I would say, also the oldest, one of the oldest association on aerospace engineering. And AIDA is promoting aerospace since 1920. And this year we are having our national conference, which will be in Pisa next August, September. In 2024, AIDA will organize the ICAS conference in Florence. And also we are working to candidate Milan as a host city to host the International Astronautical Congress. So stay tuned. We also have a journal, which is Aerotecnica Missili e Spazio. And Aerotecnica is published by Springer, and it is a very old journal. Is 100-year old, and this year we are celebrating the volume number 100 indeed. Okay, but let's talk about composites. Marco has already discussed the importance of composites in the aerospace field. As a group in MUL2, we have been working with Embraer over the last decade, approximately, on the design of a full composite wing for a regional aircraft. And we have put together a series of tools, also with the support of international institutions, universities, and of course Embraer. And we have demonstrated that by using composites, you can reduce the weight of your structural components, of your structural parts, of the 30%. This is a similar result, which is also obtained in more important aircraft, such as the 787, and we have somehow demonstrated that the capabilities of composites to be lightweight can be somehow scaled also to smaller aircraft. Well, you know, aircraft industry has taken advantage of composites at a great expense. Just to say, 2 decades ago, composites was hand layup and was cut by hand by highly qualified technicians who were able to deposit up to 1 kilo material per hour. Today, we can make massive use of composites in aerospace, mainly because of 2 technologies: the automated fabric placement and the automated toe laying. These 2 processes are functionally very similar. In automated fabric placement, you are placing multiple individual fibers onto high-speed mandrel. On the contrary, with automated toe laying, you are laying up tapes of unidirectional material. In this table, you can see the main applications of these 2 technologies in aerospace. You see that most of the aerospace, most of the aircraft programs, they make already use of this technology for fabricating what we call classical composite materials. And with classical in this presentation, I mean straight fiber composite materials. Now in this video, I don't know if you can see the video, will be very, very fast. You can see a process of fabrication of fuselage panel. And you see that in this technique, you essentially use an automatic robot to deposit fibers along given straight paths. And you will deposit a layer by layer. That's why these processes are also said to be additive manufacturing processes. So it is very maybe controversial, but I think that also 3D printing is playing a role. Well, we are currently observing, let's say, a downstream use of composite materials because of this desktop technology. This technology is very different from AFP and ATL, but we are going in that direction. And we are printing today composites at home by using this technology. Essentially, we make use of fiber fuse deposition, but you can also use different technologies. Every day we see new technologies, and there is a report that says that 3D printing of composites will grow into nearly $10 billion in the next next decade. So in this video, for example, we are printing a nylon carbon composite panel for a CubeSat here in our lab. These new technologies, so 3D printing, such as those we have discussed, or automatic tape laying and fiber placement, in the last decades have shown a new application, which is the variable angle toe composites. In variable angle toe composites, essentially you have always different layers of material, but in each ply, the fibers are relaxed along curvilinear fibers. So they are not straight anymore, but they are curvilinear. In this application, we have demonstrated, researchers have demonstrated that if you are able to design properly these fiber paths, you can still improve the lightweight of your design. And NASA scientists, for example, have designed a variable angle toe wing. They have built this wing, and they have demonstrated that you can have a saving in the weight, which may be up to 50% of a metallic construction, with a save in fuel burn, which is approximately 9%. The idea is not new. The idea of variable angle toe composites is not new. It dates back to early 90s, where Heyer and Lee have demonstrated that you can relax the stress distribution around holes by using these curved patterns, these curved fibers. But there is a drawback. Of course, now we can build these composites. This is, for example, a very new technology, rabbit toe shearing, developed at University of Bristol, and then they're continuing to study this process, in which you can essentially steer your carbon fibers along curves. And this is one of the best processes to develop this kind of structure. Anyway, if you use rabbit toe shearing, automatic fiber placement, or ATL, still you will be facing defects. So as you may imagine, steering brittle fibers, because we are talking about carbon fibers, we are talking about glass fibers, so brittle materials. Well, steering brittle fibers is not easy, because you need to do this process at the correct temperature, with the correct curvature ready. You need to preserve temperature and pressure and so on. This is rarely controlled over an additive manufacturing process. As a consequence, you will have a lot of unexpected defects. So in the right part of these slides, you see that some of the defects which are well documented in the literature. So you may have gaps and overlaps between fiber depositions. You may have a geodesic low path or curved toe path. You may have toe kinking and so on. All these defects, of course, finally will affect the mechanical behavior of the final component. And at the moment, most of the design tools for the fabrication and design of this kind of variable angle toe composites do not take into account these defects. So when you go into an optimization process, inevitably you will find maybe just a few local minima. So you will never be able to optimize your structure in the best, most optimal solution. But you will usually find a low minima because you are not taking into account these defects. These defects indeed are a function of the material signature. They say, manufacturing signature, which means the machine design parameters and fabrication procedures. So this is what we are essentially doing in our ERC project. We are trying to develop a platform for the optimum design of variable stiffness composites obtained by industrial processes, but also printing manufacturing processes. And what we are trying to do is to develop new models for carrying out stochastic uncertainty analysis. So we are providing tools to define the mechanical characteristics of variable angle toe composites, starting from the manufacturing process. So starting from the defects. With this stochastic analysis, you can go into a design for manufacturing process and build optimization algorithms for finding the best optimal solution of your component. This platform is based on CUF. My colleague has already discussed widely on our software platform. We are developing this tool since decades. Professor Cinefra, she's one of the main contributors of the Multu software tools. So there are many people working on that, and in this slide I'm just showing the latest capabilities. Of course, variable angle toe, but we are also working on elastoplastic analysis, hyperelasticity, computational fluid dynamics, and multi-field problems. But I will skip the main theoretical aspects, and I will jump to a practical example just to show you what does it mean to make multi-scale stochastic analysis of variable angle toe. In this slide, we have a rectangular plate fully clamped along the edges, and this plate is subjected to a uniform pressure on the top face, and we have just 2 layers of variable stiffness of variable angle toe plies. In this slide, you see what we call the stress state, the stress distribution within the thickness of the plate. So you see that in general, for these structures, as Professor Petrolo says, you have 3D stress states. So you cannot neglect any stress contribution, but you should take into account all of them for doing consideration on failure. And usually the stress state is complicated. And in variable stiffness composites, it's even more complicated because the property of the material is changing not only in the thickness direction, but also pointwise in the in-plane direction. So this is the nominal stress state of our variable angle toe composites. In this study, we have been investigating the effects of fiber misalignment. So imagine that your printing machine is not able to follow correctly the fiber path, and somehow you will have fiber waviness, fiber misalignment in the plane of your structure. There are many papers on experimental investigation of this fiber misalignment. I'm just citing one of those in which they provide a stochastic description of the fiber misalignment. In the bottom part of the slide, we have translated these stochastic values into random fields. So we use stochastic random fields to project somehow these defects on each ply of our angle toe. This is the effect of this fiber misalignment on the final stress state. So you see that solid line is the mean. The light blue area is the range your stress state may have. So you see that especially for the in-plane stress components, you may have very large differences which ultimately affect the failure of your composites. And this is the same results in terms of failure indexes. Those involved into this kind of analysis, they know very well the importance of fiber and matrix failure indexes in the design of composites. And you see that if you take into account the defect sensitivity, you may be conservative or not. As a consequence, your design will be I mean, you may design a two-way structure, or you may design a structure which is affected by failure that are unexpected. So you may be conservative or not, depending on the fiber waviness. In the next step, we are taking into account also some multi-scale defects. Professor Petrolo has shown the effects of voids. In this case, we are considering the effects of fiber volume fraction in the printing process. And for carrying out this multi-scale uncertainty analysis, we are combining our deterministic finite element models with surrogate modeling based on artificial intelligence and polynomial chaos expansion theories. And we are interested in essentially in investigating the buckling performance of variable angle to composites. So we are combining defects at the layer scale, such as fiber misalignment, and defects at the micro scale, such as fiber volume fraction. And in this slide, we are demonstrating that if you take into account the printing defects in your analysis and design, you will find large differences not only in the buckling load but also in the buckling modes. So you may be also observing mode aberration, not only buckling load variation. So for those who know about buckling design, they know that in these graphs we are showing very large differences with respect to nominal design. And this is just to give you an idea about the importance of new technologies such as Monte Carlo simulation with surrogate modeling and artificial intelligence in carrying out this large computational demanding analysis. So this is just to conclude the first part of my presentation, which is about variable angle to composites and stochastic analysis. We have been working on this project since 1 year. At the moment, we have more than 4 years ahead. And this is what essentially we are doing in our ERC project. And hopefully, we will have more new results in the future. We are working on genetic algorithms for optimization and so on. But this is something that will come later on. Another application we are considering in our labs is this one. It deals with deployable space structure. You know that space is becoming more and more popular. And so we are always kind of sending into space more and more objects within one single launch, for example. Or we are sending into space larger and larger structures. Just think about the James Webb, which is the very large telescope that will substitute the Hubble. In that case, for example, James Webb is making a large use of deployable, elastic deployable structures. These structures are made in composites. They are very, very thin, and they are thin because they allow these composite structures to be subjected to very large displacements. So they can be coiled around a mechanism such as you can see in this slide here, and then you can send into space, and when you are in the space, you can deploy your final structure. This is a solar sail, for example. Well, we have a collaboration with Caltech on these arguments, and we are working with them in the analysis and simulation of these kind of structures. Well, the most famous deployable space boom is the tape spring you have at home to measure your furnitures, right? And we have worked with the Pellegrino's group in their lab to kind of analyze this kind of deployable structure. It is not composites, of course, but it is very, very complicated to simulate. And we have investigated the nonlinear equilibrium curves. The structure is very complicated. You may observe limit points, snap back, snap through. And we have made a few experimental testings, and the results were very, very satisfactory. So we jump to composite structures. This is a track boom. Track stands for triangular, rollable, and collapsible boom. This is what you can find on the GEMS web. It is fully composites. It's made of a combination of glass fibers and carbon fibers. This is the nonlinear equilibrium path, and this is a kind of analysis of the post-buckling behavior of this structure, because of course this structure need to be coiled before the launch, but after the deployment, of course, they will be subjected to operational loadings, which may be very demanding for the buckling and post-buckling point of view. So this is the opposite sense with negative MX. So you see that in the first case, you were observing multiple waviness on the vertical flange. In this case, we have a small localized buckling in the middle of the bottom flange. Many other applications, together with Professor Cinefra, we are investigating acoustic metamaterials and lamp wave propagation with composite structures. We are carrying out works on nonlinear dynamics and also microscale analysis and mesoscale analysis of variable angle to composites and so on. But if you have any curiosity to see what we are doing at the moment at Politecnico, you can visit our website. You can find it in here. In these websites, you can also find our emails, and I'm pretty sure that we'll be happy to answer your questions now, of course, but also if you have any questions in the following next days or weeks, you can reach us, and we'll be happy, very happy to answer. So this actually concludes my presentation. It was just a very brief introduction on the topic. And so I can maybe interrupt the screen sharing. Thank you very much. Again, Marco and Maria, thank you very much for inviting us.
Of course, for me, it's always very interesting to see the updates in the work of the group that are always very big in few times. So I want to thank you first of all for the presentation. And I have some questions, but I'd like to know if there are some questions also from other participants. I don't know if Marco.
Thanks, Maria. So, Marco. So at the moment we don't have any questions, but let's wait. I have one, if I can. I don't know. Is this method very difficult or particularly difficult to couple with a fluid solver to treat with fluid structure interaction, or is basically the same of a simple structural solver? So the complexity is always related to the structure behavior, not to the fluid interaction. My curiosity is if you have any applications about FSI.
Yeah, thank you for this question, because give us the opportunity to extend a little bit what we said before. Yes, we have some applications. So we started with aeroelasticity, in which we use low fidelity aerodynamics model like DLM or VLM. And yeah, I can tell that from our experience, there are no more complicating effects into the coupling as compared to let's say, commercial codes or so. So at the end of the day, you end up with similar problems, let's say. What is good from our perspective is that you can save quite some computational cost, at least regarding the structural part of the FSI. And also, it can be useful whenever, I mean, one thing that I didn't stress during my presentation is that in most of our models, our unknowns are pure displacements. And this might be advantageous in many cases, for instance, for nonlinear analysis or for coupling with, I mean, when you have to interface the model with another model, because you don't have to, let's say, translate some fancy degrees of freedom into another fancy degrees of freedom. So you may end up by coupling pure displacement with pure displacement, and this might be useful.
Okay, thank you. So it would be also easy to couple with the immersed method, like immersed boundary for the fluid, where the mesh is not conforming to the body.
In principle, I would say yes, of course, then you have to do the thing. So from a, let's say, implementation point of view, may be tricky because of the complexity of the, but in principle, I don't see any spatial complicated effects due to our modeling. So
thank you.
No worries. My pleasure.
Okay. I have a question for both of you, because I'd like to know about the nonlinear analysis, both in the case of damage analysis and the case of deployable structures. Which kind of nonlinearities you consider, and what are the methods and the solvers that you use in the two cases, if there are differences? So just some details about that.
Can I? Okay, yes, in the case of deployable structures, we are considering just geometrical nonlinearities. In our methods, the advantage is that we are using full green Lagrange strains. So we are using the full nonlinearities. And you can do this in commercial software tools only if you use 3D elements. But we try to use 3D elements for those applications, and it is very difficult to accomplish the analysis. So in that case, it is just geometrical nonlinearities, and we are using a path following method based on Newton-Raphson. Those are classical methods available in the literature, and it's a tangent method. So we are linearizing the equation step by step. And we are working, I think that for plasticity also we use the same algorithms. And we are also working on hyperelasticity using the same methodologies. They are very robust, and we are very confident that I mean, we are on the safe track. But the most developed nonlinearities are geometrical nonlinearities and plasticity together with failure at the moment.
Okay, I asked it to you just to give the same details also to the other participants that always ask about that, about the kind of linearities you consider. Okay, for Marco.
Yeah, just add a few words. So as Alfonso said, for plasticity, that is one kind of material nonlinearity that we implemented. We use the very same framework. Something different happens when you deal, for instance, with this problem here in this slide. So this is the low velocity impact. So here we have two sources of nonlinearities. The first one is the material nonlinearity due to the damage of composite, as I mentioned. So you have a law inside your constitutive model that tells you how you have to change the material properties as the damage advance.
Okay.
Then you have also contact. contact is another source of nonlinearity in this problem. So at the end of the day, for this kind of problems, it's better to go with an explicit time integration scheme, because of convergence issue for coming from the nonlinearity in the composite part due to the damage is more robust using the explicit time integration scheme, so that you don't explicitly compute the stiffness matrix, but you integrate basically the
Okay.
And of course, there are some limitations due to oscillation and stuff like that, but this is, I think, state of the art even in other research work that you can find in literature. And also in commercial codes, you usually do this.
Okay. So it is all from my side. I don't know. I think you can we can conclude if there are no other questions with this seminar. Marco, if you want, I want to thank you again for accepting the invitation.
Oh yeah, sorry, maybe we have a question, just a second, from Davide Palumbo. I have just to give him the permission to talk. Davide, just a second. Okay, Davide, you can activate your microphone.
Okay, you can hear me? Okay.
Yes.
Thank you very much for this interesting presentation. So I have two questions. The first question is about the capability of your model to predict the fatigue damage. And the second question is about the how do you consider the defect within the component, because the defect affect the mechanical behavior of the components, but the behavior depend also on the defect direction, the defect shape. How do you consider this other issue? Thank you.
Yeah, they are two very good questions. Fatigue. Well, we should always separate metal fatigue from composite fatigue, right? So when you talk about metal fatigue, of course, metal fatigue is calculation of stresses. So if your model is good in calculating stresses, so you can use classical methods such as, I don't know, Paris, Lewis, and so on. So we have never worked on metal fatigue, but we are very confident that the model will be very, very good because we have good stress states. Composite fatigue is a large topic, and of course is related to failure progression, which is what we are working at the moment. And Marco Petrolo gave a good, I think, overview on what we are doing on failure progression. But maybe we are still far from fatigue analysis of composites, but I mean worldwide. We are confident that our model would be good, maybe a good candidate for this subject, but maybe Marco will give you a few words more later on. Just about defect analysis. Defect analysis, you're right, there are two methods generally in the literature to account for defects. One method is intrusive methods, and the second one is non-intrusive methods. In intrusive methods, you change your mathematical model, or in other words, you change the mesh, right? So you are able also to account for directionality and progression of failure and so on. The second method is non-intrusive, in which you put the defects as a homogeneous property. For example, you can use a penalty to penalize the stiffness of the material in a given point. In the results have been showing it is a combination of the two. For multiscale analysis at the micro level, we are changing the shape of the fiber. So we are varying stochastically the fiber volume fraction by changing the mesh of the fiber in the micro scale. And fiber waviness was accounted for locally by changing the shape of the fiber at each Gauss point. So it's a kind of exact method. If you want to introduce a damage, for example, in a given region, you can also penalize, which is maybe what Marco has done in the voids analysis, right? I don't know if you want to add something.
Yeah, thank you. Yeah, so basically, as you said, for voids in this case, we selected a number of Gauss points. In those Gauss points, we change the material property in order to emulate the defect. And sorry, I thought I was sharing my. So I don't know why, but I tried to change my slide, but it's not working. Anyhow, for voids, we do like that. So basically, we act at the Gauss point level by changing the property of the Gauss point where the void should be, let's say. Regarding fatigue, yeah, what I just said that our main contribution is on the structural modeling. We don't do much into the damage model itself. So usually we use damage models that are available in literature. For instance, the results I show you were obtained by using the CODAM2 model that is developed by the University of British Columbia in Canada. So from the material standpoint, we usually use what we find in literature, basically. So given a good material model for fatigue or a numerical scheme to deal with fatigue, we are quite confident that we can insert our structural part in order to improve the detection capabilities with a decent computational cost, let's say.
Okay, thank you.
You're welcome.
So Maria, I don't see any other question.
Okay.
I think we can free Alfonso and Marco.
Of course, we'll be available in case there are future questions, and on the website you can find our email addresses, so you can reach us with no problem.
Okay, thank you.
Thank you, everyone.
Please,
thank you very much again. Thanks.
See you,
Thank you, everyone.
Alfonso.
Thank you.
Thank you.
Thanks.
Bye-bye.
Also, thanks, Marco, and thanks everybody for participating.
Thank you.
I'm sure you will be contacted by our students in the next days. So,
we hope so.
Thanks for closing this cycle of seminars with this interesting and clear talk.
Thank you very much.
Thank you.
Grazie mille, buona serata.
Ciao a tutti.
Buona serata.
Ciao, buona serata.